Hello everyone, my name is Karen. I'll be talking about electrochemistry this video in PowerPoint. This video in PowerPoint will be mostly content and there's one practice problem. However, it's really important to understand definitions in order to be able to move on and solve other problems in this chapter. So let's get started. So first, let's look at a cell diagram. So we have to differentiate between an anode and a cathode. An anode is always the oxidation reaction, while a cathode is always the reduction reaction. Take note also that oxidation means losing electrons, and that's why the charge increases. However, for cathode, you add electrons, and that's why the charge decreases. You should also know that this line just separates the different ions. However, this two vertical lines means that it's salt rich. You should also note that always the anode is on the left side, however, the cathode is always on the right side. So let's go to some definitions. So standard reduction potential, which is represented by E and a degree sign here, is the potential of a reduction half reaction in which all reactants and products are in their standard state at 25 degrees Celsius. Standard tests usually have one polarity, concentration, their gases, and partial pressure are 1 bar. Standard cell potential is a measure of how forcefully an electrochemical cell can pump electrons through an external surface in standard state. And the standard state is the same one. So let's go on to the definition of a cell potential of a voltaic cell. So a key parameter of a voltaic cell is its electromotive force, which is represented by EMF. The force pushing, and this is the force pushing electrons through an electrical circuit, and it's also known as the term that we use about every day. So EMF is measured by the cell potential. So that's E of the cell. You should also note that a spontaneous redox reaction has a positive EMF. If it's non-spontaneous, the EMF will be negative. So here, let's move on to steps to determine the voltaic cell standard EMF. So first, you have to determine reduction, which is the cathode, and oxidation, which is the anode, half reactions, and so you're not going to be given like half reaction. However, you need to be able to figure that out from the equation that's given to you. And then after that, you have to find out the standard reduction potential of the cathode reaction, which is E naught of cathode. So these are values that you will not be memorizing. These are values that will be given on the exam, and you can also find them in the back of the Now, step number 3 is to reverse the anode reaction into a reduction reaction and find out the reduction potential. So for number 4, you have to follow this equation. And the minus sign takes seconds. So the cell potential is E of the cell is E of the cathode minus E of the anode. So again, the minus sign is because you reverse the anode reaction. Because you flip it and reverse it, you have to put a negative for the actual place. So let's see an example to make this more. Right? So let's say you have this equation, right? So you have zinc and you have the copper ion, zinc ion and copper, right? So you have to look here, which one lost electrons and which one gained electrons, right? So the zinc here became zinc 2+, which means it lost electrons, and the copper was 2+ and then became 0, which means it gained electrons, right? So based on our definitions, the copper is the cathode, it gained electrons, and zinc is the anode, because it lost electrons. So in order to make this fit the equation, we have to reverse the anode reaction and have the ions on the left side and the electrons on the left side and just stay on the right side. So if you look at the back of the book or your chart, you can find that this is 0.42 volts and this one is negative taking into account the reverse and the fact that we flip the equation. We use the cathode minus the negative value, the negative volts, and that will give you 1.04 volts. And that's the potential for this redox reaction. So we should know that potentials are an intensive property. So we define intensive property as a physical property that does not depend on the system size or the amount of material in the system. So some examples of intensive properties are temperature, pressure, density, refractive index, and hardness. However, extensive properties is a property that is proportional to the amount of material in the system. So it depends the amount of let's say copper or gold affects the mass, the volume, and it's supposed to say energy. But that's going to be it for this PowerPoint and video. However, later this week we will have more examples of redox reactions and how to solve them. Please let us know if you have any questions. Please feel free to stop by office hours. This week I have them, week 9, I have them on Thursday from 12:30 to 2:30. Please stop by, and week 10 I have Tuesday, Thursday,